Welcome to everyone for this last session on the specific topic of flow and its fluctuations. And today we have Jia, who will be telling us the ATLAS perspective, particularly from the large systems point of view. So before we begin, I just want to remind that usually we take the questions at the end of the talk. So the talk will be roughly of a 1 hour duration. And after the talk ends, we go for the question and answer session. In case someone has a very pressing question for a quick clarification, then you can please unmute and go ahead and ask the question in between as well. But try to keep the questions as much possible for the till the talk is over. Okay, so Jiang, you can begin.
Okay, thank you, Sandeep and Subhash, for inviting me to give this talk. To the student and postdocs who start, this in this field only recently. I actually did not prepare. I was expecting people can ask questions if they have. Anytime, if there's a question come up, they could ask question, but, I leave it up to the moderator to decide. So I did not prepare a huge amount of material with the expectation that, we can have some discussion. We're talking in this lecture, I want to discuss the flow phenomena and also the flow fluctuations. We could do this in any experiment, but so I focus, result from ATLAS, which I've been working on in the last 12 years. And you see, this experiment probably is different from other experiment in some detail, so which I'm going to discuss a bit. I'm going to limit my topic to large systems. We are able to actually also produce result in many in small systems and also in high PT sector and also heavy flavor sector, Quarconium sector. I would skip all of those, and because of the intention is really go deep a little bit on the each analysis. So my outline is that I first give an introduction. And also then introduce the flow observables, say a little bit about ATLAS detector and also the trigger. I will then go through a few selected results. And these results actually are not really like, some of them may not be very recent. And then I will say a few things about the future. So this standard picture people are very familiar with, right? This picture, where in the collision we start with atomic nuclei, which are just a collection of protons and neutrons, and they come in. They are being Lorentz boosted. I mean, they are actually they are contracted by like factor of 100 or 2,500, depending on the beam energy. So that means they look like a very thin disk. The crossing time is really short. Okay, it's almost like you are taking a snapshot of the nuclear wave functions in this duration, and the energy are deposited in the overlap region, which then reach some kind of local equilibrium, and then that is called the quark-gluon plasma, which evolve. Expand or cool down and then go through a phase transition. They hydronize into particles, pions, kaons, protons mostly, which are then detected by detector. You can insert ATLAS, CMS, or ALICE or STAR here, right? So we measure the same collision. So a few things about the important thing about this collision I want to discuss. First of all, this entire space-time dynamics, it happens really short, really fast. Okay, from beginning to the end, it finished in 10 to the minus 23 seconds. But despite the short duration, there's a huge amount of entropy production, right? Imagine in the lead-lead collation, we start with about 400 nucleons in the central collation. We end up with 30,000 hadrons if you integrate over the entire free space. And how do you produce so much particles, such a large amount of entropy in such short time? I think this is still a mystery, right? Because in heavy-ion collation, we are able to model the hadron evolution and maybe the hadronic rescheduling part, but we know very little about the initial stages. Okay, so in other words, how the energy, how do you take a snapshot of this collation region, and how do you deposit energy? And the deposition process produces most of the entropy. And this process cannot be calculated from first principle. In the hydrodynamics evolution, you actually, due to the viscosity, you produce a little bit of entropy, maybe 20% of them. Okay, but most of the entropy, I would say, is produced in this very short amount of time. And the nature of that is unknown. And this I think is one of the things that one should, a lot of theoretical effort. And also the purpose of going into smaller collation system is try to basically probe into this region. And understanding of this is very important for us to really understand the dynamics, right? Once we know what happens in the collation, and then we can talk about improving the extraction of the properties. And you can do this using many observables, but in particular, a lot of information can be gained from flow and flow fluctuations. So in the detector, this is what we see. On an event by event basis, if you go to a large detector like Atlas, each event we see the azimuthal distribution is not uniform. There's a lot of wiggles structures, and which can be is indicating there's like a wave-like structure, and which you can Fourier transform them into a flow coefficient. This is the amplitude of each component. This is the direction, and this modulation, they are seeded in the initial state. Okay, if you talk about the hydrodynamics, very importantly, we need to know what is the initial condition for the hydrodynamics, right? You write down the equation of the energy momentum conservation, but you need to also provide the initial condition for that, for solving that hydro equation. This initial condition are provided by this energy or entropy density in the initial state, which fluctuate event to event. Okay, so we actually often use eccentricity vectors as the initial state estimators for the flow vectors. Okay, we have many events. So the idea is that we can perturb the system with a different initial conditions, and we will try to measure the final state. And so the flow fluctuation comes in many different forms. First of all, the fluctuation happen from event to event, even for fixed impact parameter and a fixed number of participating nucleons. They can fluctuate. In addition, fluctuation can also happen within a single event. They could either fluctuate along the rapidity direction or along the transverse momentum direction. These people call it, flow decorrelations. Okay, so this means, in principle, due to this rich features of initial condition, we should expect to have quite rich features in the final state fluctuations. Okay, so this flow and the phase, they could, in principle, be a function of transverse momentum, rapidity and PID and stuff like that. But one of the challenges we are facing is that In the hydrodynamics, you can do this, but in reality, we do not produce infinite number of particles. And there's always this noise term, which scales like 1 over square root of n particles you have in the system. And this often smears out your signal, right? Depending on what you do on the event by event basis, this noise is dominates, could be dominates. If you have a small acceptance detector, this become even worse, okay? So the question is that how should we analyze this object and extract useful information? So let me copy this same equation I showed last slide and put it here. This is the transverse momentum spectra, okay, as function of rapidity, and also differentially in the azimuthal angle. And if I rewrite this, I have a inclusive PT spectra, right? I should write DND-PT here, and plus azimuthal modulation and rapidity modulation, PT and rapidity dependent modulation, azimuthal modulation of this momentum spectra. So I observe the amplitude and the phase into this so-called flow vector. I can rewrite this in the complex form. And the momentum, inclusive momentum spectra actually carries information about the radial expansion. For example, if the expansion is rapid or more violent, your average momentum will be bigger, right, than than otherwise. And this actually I call it the V0 because this is the zeroth moment of all this Fourier spectra, right? And so in order then to get rid of the noise, what we do is that we construct two-particle and multi-particle correlation functions. And we can take the average of this momentum spectral correlation function and average over many events in a given centrality, for example. This averaging will basically get rid of the noise, okay? All this finite number fluctuation will drop out. And this is, for example, in the two-particle correlation, one can construct a correlation, a two-body correlation, two-point correlation, and extract the two-particle Vn, right? Which is defined as the square root of Vn and Vn complex conjugate. What this complex conjugate means is that it just means that you take the cosine, you just take the Vn's. In this case, this will become a small Vn squared plus the cosine difference that accounts for the decorrelation effect. And for the multi-particle correlation function, you do the same trick, right? You just insert, n number of flow vectors, but ensure that the total coefficient sum up equal to 0 in order to preserve the rotational invariance. And in this case, you can see I have a complex conjugate here. That just means this equal to V minus n, okay? So n minus n equal to 0. So this is the well-defined observable. But for multi-particle correlation, you need to impose the global rotational invariance. And if you express them in the real form, it will look like just a bunch of Vn products times the angles, the sum of the event plane angles, okay? And so this is the basic object we could measure. And if you stare this object a little bit carefully, you can notice they actually are, simply a Fourier coefficient. If you do a Fourier expansion of the probability distribution of the Vn's and the phi n's, and this will appear as as a Fourier coefficient of this joint probability distribution. Okay, so if you understand, if you measured enough such object, you basically can reconstruct back, in principle, the event by event flow fluctuations. And so another way people also analyze this is actually starting to combine the moments. Remember, these are the moments, okay? Sorry, these are the moments you can start to combine moments to construct cumulants. And so there are single flow cumulants involving only one harmonics. And this is the usual two particle correlation, two body correlations. And this is the four particle correlations. And so you combine the 4 particle with 2 particles. This gives you a first order cumulants. And you can construct 6 particle cumulants and so on. Okay, so people probably are familiar with the cumulants. The one of the nice property of the cumulants is that they are additive, and they are also independent of the the reference frame, because the mean value does not if you talk about one body distributions, translational invariant. This actually, I would say the additive nature of the cumulant is one of the very important properties. That's why people analyze this. Then there's also symmetric cumulants, which was introduced by Alice, that involve the 2 different harmonics, just look like covariance, right? I mean, you have a correlation, you subtract the independent component from that. And so what has been measured is involving between V2 and V3 and V2, V4. And then we also have this asymmetric cumulants. We call it asymmetric cumulants, but initially we call this event plane correlators, which not only involve the amplitude, but also the phase difference, okay, between the different orders. And we measured many of these. Recently, there's also discussions or proposals and actually also measurements on the mixed correlations between the flow and the radial flow, right? So you start thinking about the PT fluctuation. This is sort of like a radial flow fluctuation. You can construct, you can actually try to measure the correlations between the flow and the PT fluctuation, or you might just focus on the PT fluctuation themselves, okay? And so I actually will not have time to discuss this new development, but it's a very important topic. So let me go to the atlas. By the way, are there any questions? Okay, so let me go to the atlas detector. So what is atlas? Atlas actually is the largest detector of all the LHC experiments. It is large because most of the space actually are taken by the muon spectrometer. You can see all these panels here. These are the muon spectrometers with a lot of airs in between. There's a toroid magnetic field. So most of the space are actually taken by the muon spectrometer, okay, which measures obviously the muons, which are very important for the standard model and beyond standard model physics search. In the middle, there is, if I take the middle part and zoom out here, this is the calorimeters, okay? So we have a electromagnetic calorimeter in this yellow brownish color, and we also have hadronic calorimeter for the rest, okay? And it covers very broad range, from ±5 in pseudo rapidity with very good segmentations in the eta and phi direction. So for us, it's actually very important. We have this forward calorimeter, which provides a centrality and the event plane determination. And also down the beam pipe, we have a 0-degree calorimeter, which also are very important, okay? And they provide, for example, rejection of the pileup events, selection of ultra-peripheral collisions, determinant of the event plane. They are very important. Inside here, you see the blue rectangular here. This is the region for the tracking detectors. Okay, those are mostly is a pixel and strip detectors. The tracking covers ±5, 2.5 in pseudo rapidity. For tracking, it's always important to have a very good spatial resolution, right? in both the radial direction. We typically people call it R times phi direction. Basically, is the spatial resolution in the azimuthal direction, and also the Z beam direction. This resolution is somewhere around 10 times 90 micrometers. Okay, this allows us to have very good momentum resolution. Okay, so let's see. This is a unit of GeVs. So that means for let's see, talk about 100 GeV particle, right? This will this is about 30%. Okay, no, sorry, 100 GeV particle. This spatial resolution dominates the first term. This second term is a multiple scattering term. So mostly, if the high momentum, you're dominated by the intrinsic resolution. Multiple scattering is not that important. If you just write this, for example, to talk about, let's see if I can write, right? So this term is like a bending angle. How much the track bends, which you can see this is sigma 1 over PT will be like PT delta PT over PT, right? That is roughly equal to 1 over 340, right? So that means if I move PT appears here, PT square. If I move one of the PT here, this will be like a PT, okay? So delta PT over PT is roughly equal to PT over 340. So if PT is about 100 GeV, we have about 30% of momentum resolution, okay? Which is still quite good for the high momentum region. So we can also, in the tracking, we can identify the electrons using the transition radiation detector. We can also construct using the V0 decays or the K-short and lambdas. In the very low PT region, we can also use the energy loss of the pixel detectors to provide some low, hadron PID, like identifying the pions and protons below, let's say, couple GeVs. Okay, so this was actually explored in the PP collation. But we have limited manpower, so actually there are some work along this direction, but not much publications. But this is actually one of the potential direction one can pursue in the future. For the calorimeters, as I said, these have very good granularities, which are very important for measuring the event plane. CDC provide the reaction plane capabilities. But of course, for the high energy jets, it also provides a good energy resolution and position resolution. Okay, the muon spectrometer is mostly for the muons, which are important for heavy flavor and quarkonium flow. So the Atlas triggers are very important component. Okay, so when you run a modern large experiment, one has to remember the triggers is as important as your hardware. Okay, because without the trigger, you cannot afford, or you're not able to take the interesting events. And these triggers very important. Cost a lot of money and a lot of manpower to develop. Okay, so in the PP collation, for example, we can select with a combination of the level 1 trigger. Level 1 trigger means it's like directly on the hardware levels, it's really fast. And then high level trigger means it's like online computing. Okay, you have a computer farm which analyze the events and produce decisions. With a combination of this, one can select interesting events with very good efficiency and very good rejection power. 1 out of 30,000 events, okay? And this is very critical for PP and PLED collation, which have a very high rate, but obviously it's also important for heavy ion collations. And here I show you some performance plot. On this plot, you see that in Atlas we have a triggers that are selected. Select the jet, single jet above some PT, right? This is the calorimeter jet, and so the open symbol up in the peripheral collisions, solid symbol. This is in central collisions. You can see that in central collision, well, they are very efficient at very high momentum region, but there's a turn-on region, and and the central region have a shallower turn-on because there are underlying event fluctuation. Although we actually subtract the underlying event, but still there's a smearing effect going on that broadens the turn. Okay, so for the benefit of the student, let me point out, if you want to design any trigger, what you want to do is that, number one, you want to have very high efficiency in the plateau region. Okay, that means you want to select all the interesting events. You also, number two, you want to make sure the turn on is very sharp. Okay, because the events in the turn on region, very often they cannot be used, or even if they can be used, they have large systematic uncertainties because their efficiency is low, and there could also be biases in those events in the turn region. So you need to make sure this turn is really sharp. And so we also have a muon triggers. Muon triggers is provided by the muon spectrometer, and you can see in the lilac collisions, we can see the omega phi and the J psi peak, upsilon peak, and the Z boson peaks, and with different triggers, with different here, for example, this is a dimuon trigger. Each muon is about 3 GeV, right? You can see how this allow you to select events, but with quite a lot of background. But if you want to enhance the, let's say PT of the single muon, this is 8 GeV, you already suppress all this background, right? I mean, but of course, you also lose efficiency. Okay, so there are many ways you can combining this different trigger to achieve the optimal combinations of efficiency versus a rejection. We also have a minimum bias triggers in the lilac collisions, and there are many curves here, right? So what are these curves? First of all, we have these ultra peripheral events. Okay, you can see these red lines. Those are events that require 0 degree calorimeter, ZDC, and also weighting on the transverse energy. You can get some UPC events. In fact, in order to get a real UPC events, you need to do some further cleanup because the rate is pretty high, okay, which will not discuss. And then we have a peripheral trigger, means events that are in the peripheral region. You can see that we can have a peripheral trigger and the mid-central and the central trigger to have a flexibility to optimize the physics, right? Because the mean bias, the peripheral events are typically small. We can actually change the prescale relative to each other. In the ultra-central region, let's see in the top 1% of top 2%, actually this may be top 2%, top 1%, top 0.2%. We also have these ultra-central triggers. All these triggers are in the high-level trigger. Basically, you're running the offline reconstruction in the high-level trigger. You can precisely select the events with high number of tracks or high number of energies in the forward detector. And we also then on the top here, this is the correlation in the Atlas calorimeter, this forward calorimeter in the x-axis versus the energy in the 0 degree calorimeters. You can imagine this is just a number of neutrons, spectator neutrons, how these spectator neutrons correlate with the participating basically stuff produced by participating nucleons. Okay, this anti-correlation is a typical correlation between spectators and the participants. But then what you can do is that you can reject events up here. What are those events? Those events are coming from pileup. basically there are more than two collisions, okay, more than one collisions, they produce a lot of neutrons, but they do not produce a lot of energy because one of the events are actually peripheral events. So we can use this correlation to reject pilot. Down here, we have also high multiplicity triggers. These are, again, high-level triggers, which allow us to select in PP and PLED collisions events above certain number of offline tracks. You can see the turn-on is actually quite good. I mean, it's not perfect, but you know, they actually can allow you to enhance the statistics relative to mean bias by factor 1,000 or more. Okay, and on this side is so-called the UPC, one of the UPC trigger, which we select the virtual photon colliding with a lead, and this can produce high multiplicity events. So this is a combination of a UPC trigger with a high multiplicity trigger, and this allows us to select these events. So let me pay attention to my time. So okay, so let me go to some flow measurement. Okay, in the flow measurement, what is important? I don't think I need to discuss too much here, but let me just point out the basics. First of all, the flow, we should think about the flow as a two-dimensional object, right? There's X component, there's a Y component. The flow are fluctuating around some average value. What is this average value? For example, this is the reaction plane direction, okay? And so the flow is a two-dimensional Gaussian with some width here because there's an event-by-event fluctuation, okay? But in addition, there's also statistical noise, right? Finite number fluctuation, which further fluctuate, and also non-flow, okay? So one of the very important figure of merit is the ratio between the flow, the typical, let's say, root mean square value of the flow divided by the statistical smearing. This is like a resolution, okay? This is the quantity people call it chi. This is one of the important quantity. So experimentally, we measure, let's see, if you do event plane method, you have this particle measured relative to the event plane direction, then you need to correct for the resolution of this event plane relative to the true plane, okay? And how do we do that? Well, in Atlas, as I said, we have this calorimeter, which have very good segmentation. That means we can divide them into many units. Each of these small boxes is half units, okay? And this big one is like 2 units. So this is all the way from -5 to 5. We have many sub-events. And also in the tracking detector, we can do the same thing, okay? Divide them into 10 different units. And if you want to do a measurement, you can actually pick any of them and do a measurement and cross-check the consistency. Okay, here on the right-hand side, just one of the performance plot measured by the F-core. And you can see this is the chi quantity. And you can see the signal is more than a factor of 2 larger than the noise and the non-flow for the V2, okay? But of course, for V3, only in the central collision, you'll reach like a 1-to-1 ratio. And then for high order, this really decreases. But in any case, actually for the actual resolution, you can see, it's almost 1 for the V2 in the mid-central collision. But for high order, here's the analytical relation, okay? And they actually decrease very fast. So one of the things you deal with in the measurement is that detector have a non-uniformity. Because the response and acceptance is sometimes not uniform. What you should typically do is plot the distribution of the energies of the tracks in the lab frame, okay? In the laboratory frame. You pay attention to the structures. What I'm doing here, I show you the energy distribution in the forward calorimeter. And I simply do a Fourier decomposition and label different components, also their phase. You can see, you basically can calculate, the flow vectors in the lab frame and their phase. Obviously, in the lab frame, there's no flow because the flow, collation is random oriented. So this should be 0 if there's no detector effect. Therefore, if the fact that you see there's non-zero flow factor, this is the detector effect. You can see this, the position or the phase of this detector induced flow factor vector is actually independent of the centrality, okay? Therefore, this is indicating these are just a detector effect, which you can simply subtract out from an event by event measurement. This so-called flattening shift and flattening correction you can apply to make the event plane distribution flat from second order, third order, fourth order, fifth order, and sixth order. Okay, in central collations and in the mid-central collations. And once you do this, you will observe the flow as function of centrality and PT. So this is centrality, this is PT, this is pseudo rapidity. And so as function of centrality, you have these 6 harmonics. What you see is that Vn, right, rise with centrality and they then falls with centrality. This is a geometrical effect. The as function of PT is also rises and falls, right? So this is the hydrodynamic regime where the flow increases. This is the jet quenching regime where the flow decreases. The flow is actually almost flat in pseudo rapidity, all the way to 2.5 unit. This is because at high energy, the system is almost Booth invariant. Okay, so therefore flow only decreases slowly. And this shows you that the flow signals are geometric and long range. So another method one can use to measure flow is a 2-particle correlation method. What you do is that you construct pairs of particles in the same event. Means you take pairs in the same event, you construct them and plot as a delta phi and delta eta. You get the triangle shape, right? This is a convoluting 2-flat distribution. You get a triangle. It's a pure acceptance effect. And you do the same thing for mixed event, which accounts for detector effect. And you take the ratio and you get you build the actual correlation function. So if we zoom into the background distribution, if I just renormalize each delta eta slices, I see there's non-uniformities. Okay, at a small delta eta, delta phi, there's always some like 2-tracker resolution effect, HBT, and all the short range stuff, which is about 1%. But in other region, you can see there's some detector structures which is up to 0.5%. Okay, this looks small, right? But actually it's not small, because imagine your flow signal is 10%. Flow signal or 10% of flow signal, if you talk about 2-particle correlation, is 10% squared, means become 1%, right? 0.5%, it's not very small compared to 1%. So you really need to beat down this detector structure. And this plot shows you, if I take one slice, right, in these slices, how this foreground look like and how this mixed event look like. Okay, this green on the mixed event, there's a lot of structures. Okay, you can see there's a lot of structures, but once you take the ratio, you get a very smooth correlation function. Okay, and this reflecting the physics. The detector residual effect in the event mixing of 2-particle correlation, typically you have to impose the events to have the similar centrality and the z vertex, right? That's called the event mixing. And so one of the very important things this purpose is to make sure the events you use for mixed event have the same performance or same detector effect as your foreground events. Therefore, you need to make sure the events are very close in centrality, very close in the z vertex. Okay, and the other thing is that you also need to make sure that detector performance is not changing with time, right? So what we did is, for example, is we mix events that are separated by 10,000 events, 20,000, 40,000 events, and you get some ratios of the mixed event, and you Fourier transform this into some harmonic spectra, you check whether this acceptance harmonics coming from the acceptance, whether they are stable or not. All right, this is one of the things. And similarly, let me just show you that importance of the z-vertex matching. This is actually quite important because your detector granularity is very small. The performance of detector from one channel to the next channel along the z direction can change. So what you do is the same thing. You use a different z-vertex matching, like all the way from 2.5 centimeter to 1 millimeter matching, and you produce this kind of ratios, and you transform into Fourier transform into a harmonic spectra. You look the spread, the dependence on this z-vertex binning, and we assign a systematic uncertainty of 2 times 10 to the minus 6. Okay, this translates into if you take a square root of this, it's about 0.1% of the on the flow level. Okay, so that's the precision. And so this allows us then basically take the construct a correlation function, do a Fourier transform to get the harmonic spectra, and all the way to very high orders. By the way, this is done in 2012, and we assign the systematic uncertainties. Okay, so I think one of the interesting thing I want to point out, but without further details, that I think in the future it's very important to understand this short range correlation, because they are not only non-flow, because they are elongated in the eta direction. It's actually quite interesting. And also, see if you can improve the method to actually do a measurement on these high order harmonics beyond V6 and V7. All right, so let me then, I have some let's say 20 minutes. Let me go to some other more advanced topic of, let's say, flow fluctuations. When we talk about the flow fluctuations, we have fluctuation of a single harmonics, fluctuation between the event plane, let's see the angles, and also the correlations between different flow amplitude. And these are important because they actually can provide information on the initial condition and also sensitive to the details of the temperature dependence of the shear bulk viscosity. Okay, and you can see different models with different shear viscosity produce very different predictions on this event plane correlation. So this is a quite important topic. How do we measure the event plane correlations? We do the same thing as you are seeing for the for two-particle correlation, right? We just need to correlate all these angles. Remember, there's this constraint for the rotational invariance, but we need to apply the resolution correction for each angle that shows up there. Okay, in the low resolution limit, it can be written like this. Okay, so let's see, if you write everything in the true flow level, it looks like this. And we need to do this also, importantly, is that different plane are taken from different event plane. Okay, different sub-events, sorry. Okay, you need to take them from different sub-event to suppress non-flow. And the precision with which you can measure them can be estimated using this simple pocket formula, assuming a Bessel-Gaussian fluctuation. You can see that in the low resolution limit, this resolution quickly is like scales like some power of the chi, and this is the chi value. You can see they decrease really fast for high order harmonics. Okay, and so it's much harder to do this kind of measurement for involving the 6th order event plane. So one of the interesting things is that when you have a true event plane, true flow signal, you will see that you actually can using the flow signal to detect any whether there's any misalignment in your detectors. Okay, so in other words, imagine if the two angles are rotated relative to each other by a small angle, let's say delta. Okay, there's a misalignment between two of the detectors. What will happen is that you will have a non-zero sine component, and you take the sine and divide by cosine. You can see this this misalignment will show up like a delta angle times the harmonic number, like order of harmonics, right? So this is the relation. And if there's this such offset, and if there's also a flow signal, you should be able to see this, okay? And because you can use the real flow signal to align the detector, okay? What you see is that for illustration purpose, you can see that if I use a forward detector, I can calculate this ratio of the sign component, which are very sensitive to the misalignment. I can detect a small rotation between the forward detector and the backward detector. This will show you that for the second order harmonics, I see a angle of like 0.02 divided by 2 here, right? I see there's a rotation, relative rotation of like 0.01 reading. And this actually, you can see that consistently by raising the power here. And also you can see the same angle by going to higher order harmonics. So this really tells you can use flow actually to align your detector. Okay, there's no such effect in the tracking detector, but in the colorimeter, you might just see depending on the detector, you might see some misalignment. So here's the result. So we measure the correlations between second order, third, and fifth order event plane. This is second, fourth, and sixth order, and second, third, and fourth order. Right, looks like a random collections, right? But let's just look this. So we measure some signals, some of these positive, some of them are negative in these symbols. But if you run a global model, okay, this is a global model, you see that they totally miss the data. It actually goes the opposite direction. But if you run a transport model, like AMPT model, which is shown by this line here, they actually are in agreement with the data. So that means this initial state estimators is just not capturing the physics. Okay, why? The reason is because that many of these high order event plane correlations are not only driven by the eccentricity of its corresponding order, but actually, not only by this. In fact, there's also the nonlinear component, okay, which are coupling the high order flow with lower order. So in other words, you do not expect just using the linear component, which are driven by epsilon n, to capture this event plane correlation. You need to include the high order contribution. So if I just expand this, you see that this is the linear component, this nonlinear component for the V4. The nonlinear component introduces a correlation between psi 2 and psi 4. For the V5, you have a nonlinear coupling between V2 and V3, which means psi 5 is coupled with psi 2 and psi 3, right? So 5 psi 5, 2 psi 2, 3 psi 3, it shows up here, and that's the mode coupled flow. And for the V6, the story is a little bit more complex. You actually have a coupling to V2 and a coupling to V3. That means you have a coupling, let's see, correlation between psi 6 and psi 2, which is shown here, and correlation between psi 6 and psi 3, which is shown here. You can see that they have opposite centrality dependence. The reason is because V2 increases towards peripheral collision. Therefore, the coupling between V6 and V2 becomes stronger towards peripheral collision. For the V3 is almost flat as function of centrality. Therefore, the coupling between psi 6 and psi 3 is almost flat. Okay, it's much weaker centrality dependence. So let me then go to the measurement of the flow fluctuations. Okay, so what we see in the experiment is that event by event, I have this, I'm taking the central collisions. Each event looks different, okay? Single event, charge particle osmosis distribution looks fluctuating event to event. You can also see this in two particle correlations. Take this event, construct all the pairs. You see this modulation changing from event to event. We want to measure this flow probability distribution. Okay, how do we do that? First of all, let's look at this flow vector, which I showed you earlier. Imagine you need, in the collision, the orientation of the impact parameter is random. That means that the x-axis are rotating randomly in the phi direction. You take this circle, you rotate them randomly. What then you get is something like this toroidal shape, right? It's like a ring shape. And this ring shape shows you that there is a, there's average flow, this average flow then being rotated. And also this average flow are smeared due to flow fluctuation, okay? But also, they are also smeared by non-flow and statistical noise. What we want to do is that we want to unfold, take all this noise, and basically construct this V2 observed distribution back into some kind of true distribution. Okay, so how we do that? Okay, look at the flow. The flow vector contains the true flow plus some kind of non-flow and the flow, noise, and that means the measure, the PDF of the flow vector is a convolution of the flow fluctuation, flow PDF, and the PDF of the smearing. And we can measure this directly. This is the observed flow vector distribution in 2D. And this smearing function we can construct using sub-event method. Okay, subtracting sub-event A and B. This should cancel all the flow signals. So this only mostly contains the non-flow and also the noise. And so we can unsmear this guy, by the smearing function to get the true distribution. So we actually, this is the measure distribution, this is the smearing function. We unsmear this distribution to get that. This involves obviously a matrix inversion, right? It's like because there's a response that is smearing. You have these many data points. You have a smearing function. This is like a, unfolding problem, right? Which involve a matrix inversion. There is a standard way of doing this. You can read from this reference. You basically, this is called the Bayesian unfolding, which are implemented in the root framework. Is very easy to use. Everyone can try. And we apply this unfolding method. And here's the result. So this is for the V2. So the input distribution is, or the observed distribution is actually displayed. And we do the unfolding. And you can see after a few iterations, they quickly converges to the final distribution. And you can see the ratio to the final distribution look like this. After one iteration, this brown color is here, 2, 4, 8. By 8 iterations, they already almost converged. Okay, and this actually quite interesting way to learn, many different ways of doing analysis. Okay, using unfolding to study event by event flow, and you can also do this for two-particle correlation directly. And the result is shown here. So this is the V2 distribution for different centralities, V3, V4. And the V2 distribution have very strong centrality dependence. This because they have a significant reaction plane component. It looks like this. It's a Bessel-Gaussian function, while for the V3, V4, they are mostly described by a pure fluctuation because there's no V2RP component in it. Okay, and there's a different nature of the flow fluctuation. Now, if I take the V2, which is Bessel-Gaussian, right? And naively we think it's a Bessel-Gaussian, but actually the Bessel-Gaussian fit doesn't describe the tail. Okay, this is the actual unfolded atlas data. You do a Bessel-Gaussian fit, you see there's non-Gaussian fluctuation. What is the nature of this non-Bessel-Gaussian fluctuation? Well, they can be quantified using high order flow cumulants. You just take the flow PDF, you just simply calculate all these moments and construct the, these cumulants. You see that these deviation are reflected by the fact that the ratio of the high order to the lower order are not equal to 1. Okay, this is non-Gaussian tail, which are also confirmed by direct cumulant calculation. Okay. I would like maybe just I need maybe 10 more minutes if that's okay. Let me take this PDF, do one more thing. I see there are some events with a huge flow, like up to 0.2, while there are also events with very small flow. These are all in the same centrality, right? I want to understand, why the flow can, for the same centrality, can have such different values. So what I then do is do so-called event shape selection. This is pioneered by these papers here. What you do is that I want to understand the nature of the events that have a large flow and the events with a small flow. What you see is that large event with large eccentricity or large flow, they look like very elongated, while the events with very small flow should be circular. This is the global model calculation. And in reality is that we take the, the measure the flow vector, we start to chop them off, right? In this way. And then for each slice, we can measure the flow in the middle rapidity. By the way, we're selecting the forward rapidity. The measurement is done in the middle rapidity. What you see is that take the 40 to 45% centrality, for example. Events which select to have large flow vector in the forward detector also have a large flow in the middle rapidity. Okay, I can vary the flow signal in the fixed centrality by almost factor of 3. Okay, and this event, is a big difference. And so what we can do then, take these events and start directly probe the flow amplitude correlation. I can correlate events between that are selected for different V2 value and calculate the corresponding V3. Okay, I see directly anti-correlation between V2 and V3. I can correlate between V2 and V4. I see this quadratic dependence here. And for V2, V5, I see this almost linear, but a little bit non-linear behavior in the tail. So what I mean is that I take the 30 to 35% centrality. Okay, let's see, I have this blue line. I have many event shape classes. For each event shape classes, I can calculate the V2 in mid rapidity, calculate the V3 mid rapidity, V4 and V5 in the mid rapidity. Then I can correlate V2 with V3, V4 with V2, V5 with V2, and directly check this nonlinear response relation. You can see that V4 contains a V2 square component. I can just see this quadratic dependence with I, right? This you will not immediately be able to see if you just measure the cumulants. Cumulant is only one of the moments. By doing event shape engineering, you actually can see whether the functional form of this correlation, right? Okay. So let me, I said I need a few minutes. To the last topic is on the fluctuation of the flow within a single event. Okay, I call longitudinal fluctuation. Here, I show you just some cartoon. Okay, first of all, the origin of this is because the number of the geometry in the forward direction and the backward direction are not the same. Okay, because in forward direction, the geometry driven by the forward going nucleons and the backward geometry driven by the backward nucleons. Therefore, there could be a rotation or fluctuation of these flow vectors. And this event is the real event display calculated by event hydro based on the AMPT initial condition. You can see the particle distribution in the eta phi direction is highly non-trivial and non-uniform, and they fluctuate the event to event. Okay, so it looks very different, and we want to analyze this. So the first thing we do is just simply do a two-particle correlation in different eta slices. And so what do you expect? You expect not only the angle are not the same between the forward, those defined by the blue solid symbol, and the red solid sample, not only the angle are different, but also the amplitude could be different. That lead to asymmetry in the flow amplitude, and also a twist, a torque of the flow plane. This effect could happen at the same time. Okay, so this is the nature of the fluctuation. We have measured this using this basically a ratio of the two particle flow between minus eta and eta, some reference detector, and the positive eta and the reference detector. This quantity measures the flow fluctuation between minus eta and eta. Okay, and this fluctuation decreases or decorrelates the flow. Therefore, if you make this ratio as function of eta, you see there's a linear decrease of this signature. Okay, and we measure this for 2.76 and 5 TeV, and this linear dependence are quantified using this linear fit. You extract this coefficient, which quantify the strength of this decorrelation, and then you plot this as function of centrality. What I plotted here actually is two different systems, but in the case, you see that the decorrelation for the V2 is strongest in the peripheral collation and stronger in the central collation, and they are weaker in the mid-central collation. Okay, what's the reason? The reason is actually quite simple, because in the mid-central collation, you have some kind of average geometry. This average geometry is almost the same, okay? That means the decorrelation is weaker. But if you go to the central collation, the fluctuation of the forward participant and backward participant, they are almost like independent of each other. Therefore, the decorrelation becomes stronger in the central collation, but also in the peripheral collation, because the number of nucleons are smaller there. They fluctuate randomly. Okay. And we also then take the ratio of this this decorrelation.
Jiangyong,
Yeah.
I think I missed the definition of FNs.
Oh, the Fn is defined, let me see, where's my pen? Yeah, here. So Vn delta is defined this way. It's just written like this. Vn, right, is two particle Vn. And if you write it more just V2 small, no, I'm using the lowercase. I see Vn, beta ref, cosine 2 and phi minus eta minus phi beta ref. Okay, so it's a product of the two flow vectors. It's like a two particle flow. If there's no decorrelation, you just drop out this guy. Okay, it would just become like a two particle flow. And so this is the numerator, and you can write down the same thing for the denominator. And the only thing that is different is that the reference is like some kind of forward detector. Let's see, wire forward detector as a reference that provide a common reference. And the denominator, the only thing different is that one of the flow is coming from minus eta, the other flow is from the eta. So they have a different gap from your reference, right? The gap between eta and the eta ref, minus eta and the eta ref is different. Let's see, your eta ref is here. Okay.
Mm-hmm.
This is your eta ref. This is your minus eta. This is your eta, and the ratio is between this and this. You can see you have a larger gap in the numerator than the denominator. Mm-hmm. The larger gap means you have a larger decorrelation, right? Your decorrelation is stronger in the numerator than the denominator. Therefore, the ratio is below 1, and grows linearly with the gap. Does this make sense?
Yeah. Okay. Thanks.
Yeah. Sorry, I did not define this. Okay, so this is measuring the decorrelation between minus eta and the eta, right? But relying on a common reference. Okay. So now if I take the ratio of this F between the two energies, well, you may imagine, okay, these two energies are very not okay. They are different by almost factor of 2, but okay, they are all very high energy. Do we expect some difference? The answer is yes. Okay, so in fact, that for the second order, you see it's about 10% difference, and for the third and fourth order is like 15%. So what this means is that at the low energy, 2.76 TeV, the decorrelation is stronger. Okay, you can imagine your boost invariance is less, it's more valid at higher energy, right? So therefore, if in low energy, you're basically the gap between spectator and participant becomes smaller. You're compressing all this decorrelation in a smaller rapidity window. Therefore, if you compare the decorrelation measured at the same separation, it is stronger at a lower energy. Okay, so if this is true, though, I should be able to simply scale my decorrelation by my beam rapidity. I should be able to check whether I can bring them closer to each other. Okay, so I take the Fn, I assume it scales like 1 over y beam, because if the beam rapidity is infinite, then there's no decorrelation, everything is B flat. Okay, so I plug in this, I expect a difference of 8%. So if I take this and account for this 8%, I do see they almost disappeared, but still there's like a 2% difference left, and 5%, 8% difference left for high order. And the reason for the remaining difference is not very clear. It just probably means that the simple scaling is no longer valid. Okay, there's some kind of dynamical fluctuation in the initial state, which may not be simply accounted for by this beam rapidity scaling. So let me just finish here with one slide on the outlook. Okay, well, I just discussed only the basic things, but let me talk about the what is important for the future. In my opinion, we want to understand the initial condition, and we want to understand the emergence of collectivity. Okay, this is a very important question, and we really want to understand more about this the early stages, okay, of the heavy-ion collisions. How can we do that? There are two ways to do it. We need to, systematically peering into this earlier time, from large to small system. We need to do some system scan build on the success of the earlier system scan, the RIC and LHC. We need to do this more systematically. In other words, you cannot simply take a big leap, okay? The difference between PP and PLED is too big. You go from PP PLED into LED, right? The difference, you're changing too much, and you can establish the qualitative feature, but for quantitative understanding, you need to make the steps smaller. And we need to do some kind of more systematic scanning. Let's see, there's opportunity with oxygen collision that in the near future, but also in the, at least, maybe in the round 4, round 5, even maybe think about sooner than that, we might be able to do this, if the community want this, okay? And we need to basically emphasize the role of these early stages in the smaller system and see what is the nature of the initial condition, what is the role of the subnucleon fluctuation, and how the collectivity emerges, okay? Another way to do it is that we can take stock from the nuclear structure knowledge, okay? So at this moment, we don't know, we cannot calculate the initial condition, and the initial condition is constrained from the final state, all right? There's always have large uncertainty because you also need to constrain the transport properties, and there are too many parameters. What I think we should do is that we should constrain the initial condition independently using the nuclear structure input. If you look at our initial condition, there's another, it actually have another initial condition. The initial condition for the heavy ion initial condition is a nuclear structure. And there we know a lot, okay? So we should try to constrain from this side, okay? And using the ASA bars and, system comparison, especially system with a similar mass number. They should not be too different, but in the mass number, but they can have very different nuclear structure, and you can use it to test the response of the initial condition to the nuclear structure. And this will be one way to do it. And the intersection with the nuclear structure, I think is a new research frontiers. In the last years, I, together with my collaborators, we actually pushed along this direction, organized several workshops and long events, okay? Starting the January of last year and went into the summer of last year, fall of last year, and also this spring, we have this INT program, which runs for 1 month. We invite people from low energy nuclear structure, low energy nuclear reaction, ab initio calculations, and of course also the people from heavy ion calculations, and also people from the EIC, okay? Because of all the nuclear structure, different field, nuclear physics of different factions of nuclear physics, we actually meet in the initial stages, right? Initial stage is where it is what is common for different field of the nuclear physics. And I think that this, bringing all the knowledge together will be able to improve, our understanding of that. Then consequently, will actually reduce the uncertainty of the heavy ion, phenomenology. In the upcoming initial stages, the conference, there's a track on the nuclear structure connection with the initial stages. I think the submission deadline is, in a few days. I'm actually among the local organizer for this conference. So we look forward to seeing more submission on this along this direction. I think this one last sentence, all right? So very often, this is a lesson I learned in the hard way, okay? Is that my imagination or my, the thing that I dare to do is often in the early days is limited by my detector, okay? I would never think beyond my detector because that's what I think can be done. That's what is possible. But actually, if you really want to, be creative, your imagination should not be limited by your current detector. And you should think about what other experiment can do for you, or better, what kind of new detector or new opportunity you can generate in the future, let's see, in the future running. And I think discussing the physics is actually more important at this moment than, like for the future, than thinking about the cost and other practical issues. Okay, so that's all from me. Thank you for your attention.
Thank you, Jiangyong, for this nice talk. And please ask your questions now. Please unmute and ask.
I have a small question here.
Yes.
So just to go back to one of your final figures, that F, the decorrelations.
Mm-hmm.
Yeah, this figure, the figure on the right. Okay, so I just wanted to ask you, the errors are pretty big here.
Mm-hmm.
So if I'm thinking about detectors, okay, what would you like to do in order to bring these errors down to a few percent?
Oh, you can see these errors are dominated by statistical uncertainty. I mean, the systematics in these shaded boxes is very small. The limitation at this moment is not limited. It's actually limited by the 2.76 TeV data. This is like, you know, the very early, I think I was taken in 2010.
Let me stop you right there. Of course, I mean, the statistical errors are large, but I can see that the n equal to 4, the systematic error boxes are also rather large.
Yeah, the reason is because whenever your systematic uncertainty is smaller than statistical, that means your systematic uncertainty actually have a statistical component. You see, because the way you do it is you vary your cuts and you check the stability, but whenever you vary the cuts, you're also changing the statistics. Therefore, whenever you see the bar here is still like a factor of 3 bigger than the systematics, I assume if your systematic shrinks, your statistical uncertainty decreases, your systematic uncertainty also decrease. That's my naive interpretation. Yeah.
Okay. Thanks.
Yeah. So
there
there is a comments.
there is a question by Rishi. The flow correlations are not described by Glauber initial condition. Can we say that this rules out Glauber initial condition, or is there a caveat?
Yeah, it ruled out one version of the Glauber initial condition. So in other words, the Glauber contains the right idea, right? The idea is correct, but the implementation, of course, you have a lot of freedom. And one of the improved version of Glauber model is a Trento, right? I mean, in other words, think about this. Glauber model is not just one model. It contains a number of many parameters. And I will not be surprised that if you tune your parameter, you can describe the flow correlation better. But I think the other aspect is that the flow fluctuation are not described by Glauber initial condition. That also depends on how you implement the nonlinear response, the mode coupling. And so because there, the mode coupling is a final state effect.
Yeah, so I think the plot that you showed there it was mostly coming from the hydro, right? The AMPT is getting right, not because it has a very correct initial condition, but because there is an evolution which is generating this nonlinear response, right? Which anyway the law doesn't.
So the way to think about it, you know, is that you want to define a new estimator, you need to basically define it not only using epsilon 6, but also epsilon 2 to the cube power and epsilon 3 to the second power. But that already means you need to know this response coefficient, which is a final state, you know, it depends on the final state, like a shear viscosity. Yeah, so in other words, this quantity is not only the initial state. Yeah.
Yeah. Okay, any other questions? Maybe I can ask one. So this flow decorrelation data that you show, so this is for, I guess, charged particle, unidentified particle, right? So I was wondering, because this is with rapidity, and we know that the baryon stopping happens in rapidity, right? So do you expect, for example, if you look at proton, particularly say identified proton decorrelation, although this is maybe LHC, so the baryon stopping still may not be large, but you measure probably up to 3 rapidity or so. So you could see, do you think you could see some other effects due to baryon stopping as well?
I think that you raise a very good point. I think I do not expect the baryon decorrelation will be the same as charged particle. In fact, I think even that, because the decorrelation, the thing is that the decorrelation becomes smaller as you go to high energy, but this doesn't mean the difference between the baryons and mesons, the relative difference will get smaller. In fact, I would expect the baryon decorrelation, if you calculate the F2, this F2, they could well be different between the baryon for all energies.
Yeah. Okay. Thank you. Any other questions you have? Rajiv?
Yeah, I have a question. Jiangyong, a very good talk. But in the very beginning of the talk, and maybe on slide 3, you said that the Lorentz contraction is so much that the thickness is R upon gamma, right?
Mhm.
Now, isn't it true that there is something called V partons, and the limiting thickness can never be less than 1 Fermi due to
Oh,
V partons?
yeah. I see what you mean. The weak partons mostly they will leak out in the transverse direction because there's no contraction in the transverse direction. In the Z direction they can leak out, and the Lorentz factor still apply on them, but maybe their diameter is not R, but they could be bigger. Like it could be something like you add another factor in front of the R. But I would imagine the gamma factor is always the dominating one.
In the Doppler picture, there are always V partons, no matter how fast the nucleon or nucleus moving. And the scale is set by lambda QCD, I think.
Right. Yeah.
So, thickness.
Okay. Suppose you set with lambda QCD, that's like a 0.2, 0. Let's see. So let's see lambda QCD. So it's like this half Fermi. Let's imagine it's half Fermi or up to 1 Fermi. But that will then be. Should we apply the gamma factor on top of that?
No, I don't think so.
Okay, so that's a good point. So the V parton, how much energy it carries in terms of the total energy in the nucleus?
I don't know. The number is huge, but energy is low. So.
Yeah. What is your expectation?
More, I mean, as you go up in the scale of your physics, more and more energy shifts to low X because of
gluons.
So at high scale, you'll see more V partons, and they're so to say smaller and smaller in Z, in X, your K.
Right.
And that's the thing that's what smears out the pancake. That's what's bigger than 1 by gamma. It always remains bigger than 1 by gamma somehow.
Yeah. So let me think about the following way, right? I think this picture is you're probably, I agree with you, probably it's a rapidity dependent picture. So different rapidity are weighted towards different, they have a different X value. And therefore you have to consider that. So because typically in the forward rapidity, you're looking at the large X for the projectile and the small X for the target, right? So the size might not be the same.
Right. Yeah.
So the question will be whether the partons can move around in the overlap time. Are there enough time for them to, before the scattering, right? Before they involve in the scattering, can the parton move around? have enough time to change their position.
Mhm.
I think that's the question, because if they can change their position, that means they could find a different configuration. Let's say they can change the deformation, right? If the nucleons can move, you know, you could, when they touch each other, the nucleon then have enough time to change their position to pick a different deformation, then that will be a problem, right? But my initial thinking is that there's not enough time for them to actually move around. But the weak parton certainly can, but then the weak parton is probably a small part of the nucleon energy. Most of the energy I could imagine still dictated by the partons, the small x partons inside the nucleon, not the weak parton. Weak parton is the stuff that leaks out. Probably they are, you know, they could be a smaller fraction. But this requires some quantitative estimation.
Right. All right, thank you.
Yeah, thank you for the question.
Okay. Any more questions for Jiangyong?